Hey everyone, Chris here. Before we get into this week's episode, I wanted to jump in with a heartfelt thanks to all of you for listening and supporting the show. Emily and I are really excited about how Syzygy is growing, and we'd love to reach more people around the world to share the love of all things astronomical. And that's where you can help. Share us around. Tell your friends. Give us a recommendation on social media, and this really does help. Leave a review on Spotify or Apple Podcasts or wherever you get your podcasts from. I know everyone asks for that, but it actually really does help. And lastly, if you'd like to support us financially, jump over to patreon.com/syzygypod, where you can sign up as a patron of the show. I'd love to be able to spend more time producing, researching, and editing the heck out of Syzygy, and with your support, we can do that. Anyway, thanks for listening. All right, cue the intro theme. Syzygy, episode 61, Biggest Bang Ever. Yes, indeed, and welcome back for another edition of the Syzygy podcast. My name is Chris Stewart. Sitting opposite me at her table in her office, as ever, Emily Brunston. Hey, Emily.
Hello, hello.
So today, right, recently we did the sun 2 episodes ago, and then we did the moon last episode. And by the way, how's that going? Have we had any big new fancy moons recently?
We've got one coming up, 9th of March.
What's that one again?
That's a super moon. It's, what are we up to? Is it pink? Is it
pink
flower?
Moon, a super flower, pink, chaste hedgehog
Hunger, egg.
moon.
Yeah.
So that's all happening. So we've done the sun, we've done the moon. We're going to leave the local area today, and we're going to go out into the universe at large because something very big has happened. Like, really big, bigger than anything else, the biggest bang since the big one. Emily, talk to me. What's been going on?
So this is a very exciting paper which came out from Giacintucci et al.
Well done, by the way. In our endless search for pronunciation, you keep getting the crackers, don't you?
I do. We won't put in the outtakes how many attempts that took me to.
I'll just put that at the end of the show. Yeah, you did quite well on that one, though. Apologies to anyone out there, if you are listening, that you are involved in anything that we do report on this show. If we get your name wrong, we're trying really hard, and Emily does the hardest work on that. So Giacintucci, has done what?
So we've published a new paper in the Astrophysical Journal, which is really exciting. It's all about an explosion that happened that is so far the biggest explosion that's ever happened since the Big Bang.
Right. Now, when we talk about explosions, I mean, first of all, who doesn't like a good explosion, right? There's so many good things in astronomy which go bang in impressive ways. But when you talk about big explosions in astronomy, that puts everyone else to shame. No one can come even close to the kinds of things that we're talking about. And Emily, you're saying that this is the biggest one since the big one itself, the Big Bang. So shall we just start with that? How big is this?
Well, this is an interesting thing. So I've got 2 things actually to kind of disappoint you on, first of all.
Oh.
The first thing is...
Why not? Let's do that.
That this is not so much an explosion, I guess, in the typical kind of big fiery ball, lots of energy being released at a singular point in time.
Okay, so it's not that sort of standard mental image of boom, fireball.
No. In fact, this is probably much more of a slow burn that happened over tens, maybe hundreds of millions of years.
Right, so it's kind of challenging our definition of explosion, but I guess if we're limiting ourselves to an enormous quantity of energy coming out from something, then, okay, let's call that an explosion. Sure. So that's first, like, mental image has now been dashed. Fine. I can live with that. What else am I going to be disappointed about?
Well, it hasn't just happened.
Oh, I see. It was some time ago.
It happened somewhere between probably less than 400 million years ago, but maybe at least 240 million years ago.
Okay, so this isn't something where I can just look up in the night sky and say, Emily, where am I looking? And you go, yeah, see over there's Orion's belt, go over a couple, and then see that really, really, really bright thing in the sky that looks like it's going to kill us? That thing. It's not that. It's more of a, this is interesting, say astronomers. That it's that kind of
so
thing.
Yeah, it's not something that's just happened. It's something that we've just kind of been able to explore the detail of and figure out what on earth this thing actually was.
Here's some interesting data. Let's wind that one backwards. Oh, that must have been quite an episode. Okay, So now that I've extracted from my brain and thrown away this mental image of humongous boom and fireball filling the heavens, it's not that. So what are we talking about?
So, but we are still talking about things that are really, really cool.
Okay.
I mean, one of our favourite things to talk about here, SMBH.
SMBH, supermassive black hole.
Yes.
Yes. And we talked about these a few episodes back, didn't we?
Yeah, I think it was episode 54.
Yeah.
We talked about supermassive black holes that are also called active galactic nuclei.
Right. And, okay, so winding back a little bit, a supermassive black hole, cut off the SM at the beginning, you got a black hole. Black hole is where you got huge amounts of mass, so great that it collapses down beyond anything that could possibly keep it up in the form of a star, neutron star, anything like that. There's just so much concentrated in a small area that it just collapses down to, as far as we know, to the limits of our ability to understand with modern physics, a singularity. Black hole, nothing can get out of it. Light can't escape from it. Black hole. Supermassive black hole is a black hole that's supermassive, really, really big. And you tend to find these at the heart of galaxies, most galaxies.
Yeah, so we're talking about millions or billions of times the mass of the sun with these things.
So huge amounts of stuff that presumably over time has just built up and built up and built up, stuff falling into the black hole, get a bigger, supermassive black hole. Yeah. And they're called active galactic nuclei, remind us, because they're quite energetic.
Yeah. So an active galactic nucleus is a black hole that's feeding, which means that there's material that's falling into the black hole, and at the same time there's a whole lot of energy being released in that process.
Yeah, so that notion of nothing can ever escape from a black hole, true, once it's got inside, it's not coming out again, but you can have these incredibly energetic processes going around outside the black hole as matter gets torn apart in the incredibly strong gravitational fields around black holes. And so some of that stuff goes in and increases the mass of the black hole, the energy of the black hole, and some of it escapes as really, really high energy stuff flinging out into the cosmos, which has a big impact on, well, everything, really, the entire galaxy around it. So that's supermassive black holes. That's what we're talking about today?
Yes. Well, at least that's the suspicion.
Right.
Because it turns out that this particular, let's say, bubble of energy that we've found, or at least it's an absence of stuff. It's a cave that's been carved out in a piece of gas. And when you sum up how much energy it must have taken to carve out that hole, then your thoughts instantly turn to, well,
who's responsible for this?
There's got to be something like this. But the interesting thing is there's no active galactic nucleus in the region.
Interesting. All right. I sort of feel like we need to back up a little bit here. So talk us through this paper by the wonderfully named Janchitucci. What's actually been found? We found a void.
Yeah. So
what's going on?
So you basically this cavity which has been carved out. So we have a galaxy cluster, which is a group of galaxies.
Okay. So this is not in the Milky Way. This is elsewhere. This is
very,
an entire
very far away.
Long way away, whole cluster of galaxies.
390 million light years away.
And I struggle with distance scales on this podcast often, but even to me, that sounds like a very long way.
It's a very long way. And so what we've been able to see is this cavity that is huge in size, really, compared, and what the cavity is in, because if you've got to have a hole, it's got to be in something. Yeah, is in the kind of cool sort of material that's at the center of galaxy clusters. It's called kind of the cold medium or cool medium, and it's like just a bit of gas and that's just sort of floating out there between the galaxies.
Is it sort of the cluster level equivalent of the interstellar medium in our galaxy, right?
Yeah.
It's the stuff that fills in the gaps. It's not empty. There is stuff there.
Yeah.
Okay.
And it's densest, closest to the kind of gravitational central point of a galaxy cluster.
Okay.
So they've got this big clump of gas, and there's a cavity in it which is 15 times wider than the whole Milky Way galaxy.
Hang on. I'm just going to pass that sentence. So take the Milky Way galaxy, right? 15 of those in a row. That's the linear spread of this bubble of this cavity, this void.
Yeah.
That's huge.
It is really.
Holy cow.
It's really, really huge.
So what you're saying is something's cleared that, right? If you're in a crowded room and you shout loudly, people are going to move away from you rapidly. You just cleared that room. But this has cleared a void 15 times the size of our galaxy across. That's quite an extraordinary feat.
It's huge.
Yeah.
And there were some hints of this. So the first hints of it came from a couple of X-ray observations. So the first one being Chandra X-ray telescope, which is one of NASA's kind of premier X-ray missions. And that was noticed this kind of slight little curvature in the X-ray bubble, which meant that there was a sort of a gap. And people sort of at the time thought, well, this could be one of these voids. We've seen them before in other galaxy clusters. But the energy sort of got a little bit high when you did the maths. So they sort of thought, well, maybe.
So having a look at these X-ray images coming back from Chandra, let's just work that. Oh, that's really quite large.
So maybe there was another explanation, was kind of the conclusion.
Sure.
We also had some X-ray observations from XMM Newton, which is kind of ESA's version of Chandra.
Mm-hmm.
And then what the the scientists we're talking about did with today is they took that a bit further. They got some radio observations. Now, we've talked about before how you kind of have this pairing on energy scales between the very, very high energy photons, which are your X-ray photons, and the very, very low energy photons, which are your radio photons.
Yeah, I mean, astronomy is across as many wavelengths as humanly possible, right? You can look in the optical, the stuff that we see with our eyes, but you can go either end of that as far as you hopefully can. And down one end, the low energy, long wavelength, low frequency end is radio waves, radio astronomy, the big dishes. Far other end is really high energy, really short wavelength, really high frequency, X-rays. And all of these different kinds of astronomy, all these different wavelengths give you different information about what's happening out there. Often the same object looks very different through different kinds of wavelength.
Yeah.
Radio and X-ray can look very different and give you complementary information.
And you have this really nice pairing with very high energetic objects between, so high energy photons, you expect they come from high energy things. That
makes sense.
Natural,
yeah.
Right? That's true. But also in the radio, the emission that we get from in radio frequencies is often linked to really high energy processes.
And why is that?
So
because radio is low energy. We just said that. So why would you get lots of that with a high energy thing?
Yeah. So for this case, what we're talking about is a piece of emission called Synchrotron Emission, which is in itself not very energetic, but it comes from charged particles doing energetic things in magnetic fields.
Oh, okay. So, yeah, you can get a lot of the low energy stuff, a lot of it coming off when high energy things do high energy things in magnetic fields. It'll give off the lower energy stuff in large amounts. And so the radio can tell you about that.
Yeah.
Cool.
So what these scientists did was they took some beautiful radio observations from a couple of radio telescopes. We'll talk a bit more about the telescopes in a bit. And they mapped it onto the same maps that we had the X-rays. And the quote, which comes from the researchers, is it fit like a hand in a glove.
Oh.
So what you have is the radio observations, which are tracing these high-energy synchrotron emissions, are just neatly matching up with this sort of curved edge of the void.
So something's going on there. I mean, seeing it in one or the other would sort of lead you to think, well, okay, there's something interesting going on here. But seeing both says, presumably, okay, something very high energy indeed has happened here.
Yeah. And so the explanation for this is that we had this active galactic nucleus, which produced a jet. And there is a host galaxy that's sort of the suspected culprit for this, that's got a supermassive black hole in its center. And this jet came out from the supermassive black hole, hit the hot intergalactic gas, and basically created these radio emissions, and as well as carving out this void into the region of the cooler gas.
So it's a little bit like I've got a mental image of a fire hose. The supermassive black hole is sending out this fire hose of high energy stuff, which is just plowing into the intergalactic medium and doing all sorts of stuff, but it's clearing it out as it goes.
Yeah.
Yeah.
So if we put some numbers to this, because this is where the research became really exciting, was, okay, now I have to confess I got a little bit nerdy about some of these numbers.
This doesn't surprise me in the slightest. Go for it. Be nerdy.
Okay, so we've got two sides of this. First of all, there's we'll work mostly in joules because I'm a joules kind of person.
Okay.
And I get that radio astronomers and so on might not be, because most of the work is published in ergs.
Oh, well, people out there in listener land may not know what an erg is, but they've at least heard of joules, kilojoules, a unit of energy, even if it's just in the food that you eat. It's a familiar thing.
Yeah. So the published result, which is something like the pressure times volume. So this is the work that must have been done to clear this cavity.
Okay, so we can think of it as the amount of energy that has been expended in clearing out this void.
Yep. It's calculated to be 5 times 10 to the 61 ergs.
Ah, yeah, okay. That's a big number of ergs. What about how many joules?
It's the same, 5 times 10 to the 54 joules.
5 times 10 to the 54 joules. So that's 5 with 54 zeros after it. That's a really big number.
It's a very, very big number.
That's billions upon billions upon billions, but that's lots.
So here's where I got excited and thought, well, I can do some comparisons.
Sure.
Let's try and figure out,
Because I'm immediately thinking, like, how many Mars bars is that?
A lot. I didn't go that far. I went to the high energy things and tried to figure out like how many high energy things.
That's why you're the research scientist and I'm just the guy who runs the podcast, right?
So, I mean, there's a bit of rounding here, but, just on orders of magnitude.
Sure.
Let's talk about, one thing, a lot of energy might be something like the sun.
Okay, yeah.
Okay? Sun puts out lots of energy.
It does.
So if you sum up all the energy that the sun's going to put out over its entire lifetime.
Right, so not just a day or a year, but the entire, how long is that?
Like 10 billion years?
10 billion years. How much energy does the sun put out in all directions? And go
10
on.
to the 44 joules.
10 to the 44 joules. And that's still 10 billion short.
1/10 of a billion, yeah.
Yeah.
Of what this...
Yeah, like a factor of 10 billion short.
Yeah.
Wow.
Okay. So the sun's not really going to help us.
No.
Because I don't
get a grip on
really
that.
still have a good
I'm now
concept
imagining
of a billion, right?
10 billion suns for billions of years. It's meaningless.
It's too many numbers.
It's just numbers.
Okay, so we can go to the largest kind of stellar explosions that we have in the universe.
Yeah.
These are called hypernovae.
So we've gone beyond super, we're into hyper.
Yeah, we're just going to go straight to hypernovae.
Do we get ubernovae?
No, the hypernovae is where it stops.
Okay, right. You don't want, if anyone ever offers you an ubernova, don't go there. Just stop at the hyper.
And these are still only 10 to the 46 joules.
Okay, right. So that's 100 times more than the entire energy output of the sun, and we're still hundreds of millions short.
Yeah, 1/100th of a million.
Yeah, goodness.
Okay.
So we're kind of getting a bit of a concept of this is big.
I've got one more, if that helps. So we've talked about LIGO, the gravitational wave detector, and how when things like two black holes merge together, enormous amounts of energy are put out.
Now that was the whole thing about LIGO was we're detecting the ludicrously small wobbles in space-time that have travelled across the cosmos from ridiculously energetic events far, far, far away that moved space-time enough, wobbled it enough that we could detect these incredibly small things here on Earth. I mean, that was the whole point, was you needed the biggest bloody things in the universe in order to be able to detect them. Are you about to tell me that this is even bigger?
It's bigger than a hypernova,
right?
Which is good news because we're getting closer to our AGN. So the largest black hole merger that LIGO has ever observed put out something like 10 to the 47 joules.
And sorry, the one that you're talking about that cleared this void was 10 to the 54.
Yeah, so I'm afraid it's still only 1/10 of a million.
So this is big.
Yeah.
This is a really, really big thing.
Even
whatever
on
it
astronomical
was.
scales, this is big. And at this point, I have to confess, I kind of gave up because the only things that are bigger
what's the point?
That come close are things like if you took the entire mass energy of the galaxy.
Yeah.
And I don't think that's...
we're
very useful concept at this point.
If you can't take the biggest things that we've ever measured banging together and causing, gravitational waves to be detected on Earth, if you can't take that and turn that into, so it's, 3 of those, it's still 10 million of those. Yeah. If that doesn't make any sense, I think we've got nothing to compare it against. Okay, so what we're left with is, wow, that was big. So we kind of then need to return to, what the hell was that? So you were describing before supermassive black hole sending out huge jet, clearing out fire hose style this big void. But that's an extraordinary amount of energy. Is there any sense of how, why, what happened?
Well, we do have some other examples of this, and this is where I also got a bit nerdy about the numbers because I was, back checking through different astronomical papers and getting a little bit too into it, shall we say. So we do have another contender. So the event which this beats, if you like, which it beats by something like 5 times in energy.
So previous record holder.
Is something that's fairly similar. It doesn't have such a good name. So the one we're talking about is actually happening in the Ophiuchus galaxy cluster, which is in the constellation of Ophiuchus. It's interesting. The other one that it just broke the record of, and maybe this is a good thing, was called the MS 0735.6 plus 7421 galaxy cluster.
Yeah, it doesn't exactly trip off the tongue, does it?
No, it's a bit closer. It's 2.6 billion light years away. Sorry, a bit further, billion light years. Mm-hmm. Yeah, the other one's only a few million. Yeah. But it is one of the largest supermassive black holes that we've ever found in this particular MS galaxy cluster. So when we're talking about a black hole in this cluster, that's at least 10 billion times the mass of the sun.
Wow. So big.
Yeah.
Very big.
Big means you've got a lot of energy to throw around, right? So this particular event has got a double cavity, which is really nice. It helps you identify. So because you've got jets that come up not just above the black hole, perpendicular, if you go pointing up, if you like, whatever way up is.
Imagining a black hole spinning around, jet coming out above and down below.
Yeah, you also have one pointing down. So there's a double cavity in this particular. And similarly, they've seen the radio emissions and the two sort of holes that have been carved out in the X-ray emissions as well. So that's a really interesting object. And so that one, is only 1/5 of the energy. And that's a very, very large black hole. I think what's interesting about this current one that's just been found is that you've got to now multiply your energy levels by a factor of 5. So if you want to sort of calculate how much mass has fallen into your black hole to produce this amount of energy, then you're going to have something like, 5 times 600 billion suns.
Okay. I'm just going to pull this apart for a second. So you're saying that in order to produce the amount of energy that we can calculate has cleared out this void, right? This big one that is now the world record holder. You would need, because that energy is coming from mass which is falling down into the supermassive black hole, which is already supermassive, like it's just huge beyond belief.
Billions of suns.
Billions of suns. And just to put that in some kind of perspective, how many solar masses do we think there is in the entire Milky Way galaxy? Like it's
lots,
but hundreds of billions, right? Okay, so we're talking, a significant fraction of our entire galaxy's worth of stuff already in supermassive black hole. Fine, but you're saying you would need 5 times
600 gives you 30,000 million, so 3, nearly 0.3 of a billion.
Has fallen into the supermassive black hole, of which there's then created a whole pile of energy to go out and clear this void. That's an incredibly large amount of energy, large amount of mass that we've just swallowed up into that supermassive black hole. That's crazy talk.
Yeah. Everyone's thinking that this is maybe not exactly quite right.
Okay.
Because
is that because we're starting to get up into numbers which are just, now hang on.
Yeah. Pretty much.
How would you engineer such a thing?
Now, let's take a step back and sort of be appreciative of the fact that the physics near a very, very large supermassive black hole are weird.
Yes.
We don't understand everything that goes on with these accretion disks and how the energy production is actually going on in these jets. So, there's an amount of uncertainty there. I've seen a reference, and I didn't go and read it in detail because it looked very, very scary and very complicated. But there might be some things to do with rotation that become important at these very, very high mass energy releases.
Right.
However, putting all that aside, it's not kind of an event where a single star got consumed by this black hole. Right? No. You're talking about a lot of mass. So one hypothesis which was put forward was that, maybe this is not just a star. Maybe this is kind of a big dump of gas that came in. And the origin of that big dump of gas may have actually been another galaxy.
So what, like a galactic collision? That kind of thing?
Yeah. So galactic cannibalism, shall we say, happens all the time.
Yeah, that's an actual term, isn't it?
It is, yeah. So galaxies merge all the time. They're relatively close in space, and in clusters that's even true. There's lots and lots of galaxies in a relatively small proximity. And so the galaxy mergers happen often, and either you get flybys and you get gas being stripped out of one galaxy and
it's going to happen in however many billion years' time, isn't it, with us and Andromeda? Aren't we going to sort of have a big super galactic collision, which we probably won't even notice because there's a lot of space there. There's a lot of distance between the stars.
We're going to become Milkdromeda.
Yeah, we did talk about that. But what you're saying is, even though it's quite possible for the sun and our solar system to be completely oblivious other than a really interesting night sky transformation over very long periods of time, if a bunch of gas in a galaxy that you're colliding with gets quite close to the stupidly large supermassive black hole in the center, it could gobble it up and have quite dramatic consequences to the surrounding area.
Exactly, yeah. And we know, well, we have very good evidence that these kinds of galaxies that we do find close to the center of clusters are already products of mergers, maybe of several galaxies already, because they're huge in size. They're called enormous CD galaxies. They're just enormous blobby things. They're not like your beautiful spirals like the Milky Way or Andromeda. They've kind of lost all that structure and
because of the collision,
mergers,
because things just get really messed up.
So if you had another merger to that, you dump a whole lot of gas that may have been sort of put into the black hole. Okay, you can probably generate enough energy for this event.
Wow. And as you say, it's we talk about this as an event, and I've still got this mental image of boom, a huge explosion. But this is stretched out over a significant period of time. This is gas matter falling into the supermassive black hole and being released in I guess by cosmic standards, a relatively short period of time. But by our standards, very long periods of time.
Yeah, so probably a few 100 million years.
Yeah, which is a very long period of time. So an event is an interesting notion that an event in astronomy can be over a very long period of time.
Yeah.
And it's still an event.
Event has switched off now because we don't see the evidence for the active galaxy in the current data. So that's quite interesting in itself as well. It shows some dynamicism of the central galaxy.
Yeah. So, but did you say that there is a candidate that that astronomers have spotted? That one. It was probably that one.
Yeah.
And that's because that one is really big.
It's really big. It's close to the center of the cluster. It's close to the center of the kind of cool gas cloud that we've been talking about, the X-ray gas clouds. It's a little bit offset, which models may well help us to understand if that's the fact that it's offset. And the term that's used a lot in the paper was called sloshing. So instead of sort of having your galaxy at the center and then a lot of sort of cool gas surrounding that in the intergalactic medium, it's a bit shunted across. And maybe even the AGN explosion, if you like, could cause that. Or maybe the reason why we don't see the other jet is because of that offset. So there's quite a few maybes about this individual system.
Right. I mean, it's got to be a very difficult thing to study when there aren't a lot of examples of this. So you said that there are others. We've seen this sort of thing before, maybe not quite as big, but you've seen it before. But it's not like there are loads of these things that you can gather huge amounts of data on and go, well, we know exactly what's been going on here. No, you don't get things of this scale terribly often. And so there's probably a lot of guesswork going on as to what's actually happened here.
Yeah, so there's a distinction between the measurements which you can make that are super accurate and kind of the things that you might say, well, here's an explanation which is sensible enough to produce the observations that we see.
What do we infer from this? What can we understand from it? And could be this. This could have happened. That would explain that. I mean, that's how science works. It's, can your hypothesis explain all the things that you see? If it can, great. Well done. Doesn't mean you're right, but it means it's a pretty good explanation. Yeah.
And those observations continue, and they're going to continue on similar systems because, like I said, we had the Chandra and XMM Newton observations, which were the X-rays, and then this group followed it up with two really interesting sets of instruments. So, we can chat a little bit about them because they're quite cool. Yeah. The first one is the Murchison Widefield Array, which you might have heard of.
Down in Australia.
Yeah.
Yes.
Yeah, so it's in Western Australia. It's really interesting. It's a radio telescope, but not like what even astronomers tend to
it's an interesting one, isn't it?
Yeah. So it's a low frequency radio telescope, and so for that you don't need a dish even at this point.
Yeah, because your classic radio telescopes are dish-shaped. And you get even the really, really big ones, which are embedded into the sides of mountains. They're so big, 100 meters across or more. But big dishes. But this is different. This is not dish-shaped.
No. So these ones are they're kind of a bit odd, really, to look at. So what they are, you've got a 4x4 meter kind of grid, a little mesh that you put down. And you put something like 16 little antennas on it. And each of the antennas kind of looks like, this is going to be like a little starfighter.
Right. Yeah.
Yeah, like a little kind of, you've got a central blob in the middle, and then they've got little arms that stick out.
Yeah, like a Star Wars X-Wing or something like that.
Yeah.
I always think when I see pictures of them, they kind of look like little spidery things, like robot spiders. But maybe that's just me having lived in Australia for a long time.
So
anyway,
they
don't look like radio telescopes.
No.
Yeah.
But that's what you need to do when you do move to low frequencies. There's no point building a big dish, really, for these things. You just need the little antennas.
Right, because low frequency means really big wavelength. And so, am I right in thinking that wavelength and size of dish are kind of important? That if you want to get down to really low frequency, really big wavelength, you'd need a really, really big dish in order to collect things of that wavelength. But it's much easier to say, well, no, we'll just put effectively a bit of the dish over there and a bit of the dish over there and just spread them right out, because it's not the dish that's important. It's having things that can pick up things over that scale.
Yeah, exactly. Yeah.
Yeah.
So you're just sort of transitioning through different sort of technologies for different bits of the spectrum. So the whole, for the Murchison Widefield array, the whole thing comes up to something like 500 meters squared.
Mm-hmm. Which is big.
And what's quite interesting is that this one is a precursor for SKA.
That's right. Now, the SKA, the Square Kilometre Array, which it's in the name, really, isn't it? It's an array of telescopes. Some of them are dishes, some of them are not. Some of them are little spidery things. But the entire thing spread over parts of Australia, South Africa or Africa, bit in New Zealand as well, if I'm not mistaken.
Fingers crossed,
Yeah. But over a very, very large area, but spread right out. And some of it in really interesting sort of spirally patterns and stuff as well. The total of which would be equivalent to one big square kilometre of dish. Is that the idea?
That's exactly the idea.
And that's being built now.
Yeah.
Yeah. That's going to be exciting.
So
and this is a precursor to that. It was sort of let's do this as a dummy run and see if we can make this work.
Yeah, so it was part of Australia's bid to host it as well. So it's an important array. The other telescope that was used is also one of my favourite new ones that I've found out in the last couple of years. It's the Giant Meter Wave Radio Telescope.
Okay, I'm not sure that I've heard of that one. Tell me about that.
We have mentioned it before.
Have
it's
we?
in India. It's near Pune in India.
Yeah.
It's a great telescope. It's 30. Now, this is back to dishes. So it's 30 individual dishes, each of which is 45 metres.
Wow. Okay, that's quite big. And 30 of them. One of those individually is not small, but 30 of those together working in concert.
Yeah.
That's quite big.
It's a fantastic instrument. And what's interesting, what links it all together as well, is that the Giant Meter Wave Radio Telescope is also a pathfinder for SKA.
Now, what does that mean? It's like, similarly, it's a precursor. It's sort of...
Well, it turns out there's two definitions. So precursor means that you're a sort of telescope that's sited in the same place where SKA will be.
Right. So you will form part of that, or at least part of the infrastructure for the SKA.
Yeah.
Yeah.
And Pathfinder means that you're like a technological step as part of the development.
We're testing some stuff out.
Yeah.
Yeah. Okay.
So that's really cool.
Yeah.
They're both linked together. So I did have a quick check on the updates for SKA because SKA has been on the cards, since I was an undergraduate at least. It comes and goes.
I remember a big flurry of announcements. How long ago, when was it sort of announced where these things were going to be? Because it was a little bit like the Olympics. It was sort of we're putting in a bid and you're putting in a bid and someone's going to win to get the sighting of the SKA. And the announcement was basically, well, actually, you're going to have some and you're going to have some. And New Zealand's going, we'd like some over here as well, please. And it was kind of spread out a bit. But that was when, like sort of 10 years ago?
Oh, it must, maybe not that long, but somewhere between 5 and 10, I would say. Yeah.
And then it's kind of gone a little bit quiet in the press because, well, now they're just getting on with it, right? There's a lot of construction and work going on.
Well, okay, let's remind ourselves that SKA is probably the most ambitious telescope ever.
Yeah, and it's not just the building of the spidery bits and the dishes. There's a back-end infrastructure of computation and information storage and transfer, which is off the charts.
The amazing thing I love about the SKA is that this is a telescope that relies on Mouse's law, which basically says that your computing power is increasing at an exponential rate as time goes on. It relies on that to be able to exist.
Yeah.
So it says, okay, our telescope's going to be up and running. I mean, current forecasts are late 2020s, early 2030s. When it comes up online, we have to project that computing power has increased by enough so that we can actually run this telescope.
That's right. I remember reading about it, and they're just sort of saying, look, we don't have the capability to do what we need to do now. You know, we're building with future in mind. So computer scientists, if you wouldn't mind just continuing to do what you do, or even a little bit faster, actually, would be awesome, because here's our demands. And the demands are something along the lines of the entire traffic of the internet in, I think it was like 2015 that I was reading about this, the entire 2015 internet every day. You know, just stupid amounts of information being thrown around. And yeah, we don't have the systems, we don't have the processes, we don't have the architecture to do that. That's what's happening now.
Yeah, and we need to be able to analyze it and reduce all the data on the fly, because we don't have a possible way to store it.
You need to be able to sort of figure out this bit, we keep this bit, now throw that bit away, all of that entire 16 internet's worth of stuff. Just get rid of that, we'll keep this bit here. It's off the charts. And that, to me, is what is so fascinating about modern astronomy, is that there is room for so many different kinds of people. Right? We really need really good astronomers, astrophysicists, people who can work out the physics of what we're looking at. We need people who can do the IT, both from we need to manufacture chips to do the exact thing that we need to do, right through to I'm good at algorithms, fantastic, we need you over here, now, go. There are so many different roles in astronomy now that goes so far beyond your traditional astronomer. It's just not funny. Yeah. If you're interested in this stuff at all and you do basically anything, you should probably be knocking on the SKA's door at this point.
It's amazing. And I love the ambition of the whole project. But, you know, that ambition does come with some downsides. So I think that it maybe hasn't progressed quite as quickly as what everybody wants.
Right.
Some sort of intergovernmental difficulties have been cited.
What a surprise.
We won't go any further than that.
Right. Fingers crossed it will continue to progress?
Well, the good news is the first contracts to start building stuff should be handed out by the end of this year.
Right.
So we really should be actually having bulldozers on site, hopefully by the end of 2020. And current forecasts are for a first light, first test, maybe not with all of it, but with some parts of the array in 2027.
Okay, so they were, that doesn't sound too far off track. Weren't they talking early to mid-20s initially? Wasn't that the plan?
Yeah, so we slipped by about a decade so far, but, you know.
Oh, I see. Okay, right.
Not too bad.
Well, you know, when you've been talking about this for a couple of decades already, what's another decade? It's a little bit like the James Webb Space Telescope. Come on.
Oh, don't. Oh, no. No, we don't want to blame poor James Webb for this stuff.
Sorry, James Webb.
Yeah, so it is very exciting. And it's an exciting time to become a radio astronomer, because you're going to have an instrument in your future, which is going to be thousands of times more capable than anything we have today.
If you're listening to this and thinking, I wonder what I should get into in my future career as you're, churning your way through high school or even just starting a university degree, radio astronomy has got, they're going to need a lot of people. And as I said, across a whole range of fields. There's a lot of stuff that needs to happen there, which is a nice position to be in astronomy, because I can remember talking to a lot of astronomers over the years in decades past about, there's only so much room for so many astronomers in the world. If universities are churning out lots of people with astronomy degrees, we probably need to talk to some of those graduates about what they're going to do next, because there's not a lot of positions coming up in universities and research centres. Whereas this is kind of, actually, no, we're going to need a lot of people. You may need to think a bit about your particular skill set, but there's going to be a lot of people needed.
Yes, it's very, very exciting.
Yeah. Okay, so that's a bit of a digression on the SKA, which is just such an exciting project, and not just because so much of it is based in Australia, and I'm biased, but we need to bring this back around to the whole point of this episode, which was, if you remember from like 10 minutes ago, huge amounts of energy creating gigantic voids in galaxy clusters far, far away. So I guess it's fairly standard on this show, Emily. We kind of got to bring it back around to, great, okay, beyond the headlines, what does this do for us? What do we learn from this? So what? Okay,
so astronomers sometimes get a bit of a rap for being what we call stamp collectors.
Right.
So that means that you just want to go out and find all the things and put them into categories.
And the rarer the stamp, the bigger the stamp, the more energetic and explosive the stamp, the better.
But that definitely isn't astronomy. I mean, yes, we might have an astronomical Guinness Book of Records,
sure,
if you like. And this entry is an exciting new thing to put into that. But there's a lot of physics that's going on here that's very interesting. I mean, before we even consider the interesting physics that goes on in these extreme environments near black holes, these extreme energy sources that they are. I mean, there's a kind of overall arching parts of galactic evolution and indeed evolution of the entire universe that rely on information about these kinds of events.
Yeah, I guess that's right, isn't it? Because there's only so many ways that you can directly investigate incredibly high energy things, which, as you say, on the one hand, it's, well, great, you just found the most high energetic thing. Well done. But the flip side is, no, but we need to find these things because we need to understand what happens under those circumstances in order to understand the rest of the way the universe came into being and has evolved.
Yeah.
And there's only so many ways you can do that without guessing entirely.
Yeah. And we certainly know there's only so many ways that you can get energy out of galaxies, let's say. We talked about before, and we talked about how one galaxy was triggering starbursts in other galaxies.
Yeah, which was very cool.
Yeah, so this is basically the only way we have of directly pumping out energy back into the intergalactic medium. So it's really important we understand this to understand the dynamics of how galaxy clusters work and where the energy actually is. But from a cosmological perspective, if you want to understand the whole evolution of the universe, again, you've got to kind of figure out where the energy is going.
Yeah, that's a big one in the evolution of the universe. It's basically all about the energy, isn't it?
Yeah, mass and energy, and the back and forth that they slosh between those two. And so if we don't have a good idea of what the biggest energy dumps we have into the universe are, then our cosmologies are not going to be super accurate.
Yeah, and there are only so many ways that you can do that without really focusing on, all right, so we've got to be looking at this at the scale of the biggest things that we have, and we've got to be looking at the scale of the most energetic things that we've got, because that's where you're going to find things of this scale. You're not going to find it in your local, Milky Way neighborhood. Oh, look, just over there, this incredibly energetic thing. It's on scales almost bigger than we can imagine. But that's where you've got to look in order to find this information.
Yeah. And although these events might be super rare, these types of objects might be really, really rare in the universe. The fact that they do put out so much energy makes them significant.
Well, that's it for another episode. An episode about really big explosive things. I'm not sure what the progression is from here. We did sort of sun, moon, now massive, supermassive black hole explosion-y type things. I don't know. Maybe we'll go with something a little bit gentler next time. What do you reckon, Emily?
Something that's super exciting, though.
Yeah. It'll be good. Listen, we've got something coming up. Speaking of very exciting things, on May the 16th in Hull, there will be the first ever Northern Podcast Festival, and we're going to be there. And if you want to come and see us live, then you should be there too. You can go to northernpodcastfestival.com and find us and buy your tickets. You can buy them right now for the very, very low and quite stupidly precise price of £2.67, which is just a bit silly. But there we are.
267p's.
That's right. Bargain at any price. So come along and see us. We'll be nattering about all sorts of very cool spacey things at the Northern Podcast Festival. We would love to see you there. Otherwise, if people want to get in touch with us and say hi, Emily, how do they do that?
So we are on Twitter.
We are
at SyzygyPod, SyzygyPod.
That sounds familiar, actually. I think we have that name on other places as well.
It's like it's a theme.
Yes, indeed. Instagram, we do the occasional Instagram post. We're not on the Snapchats and the TikTok, but Facebook, you can find us on.
Yes.
We are on Facebook. And, of course, we have a website.
Beautiful website.
Syzygy.fm, where you can find all our past episodes, show notes, pictures, etc., and a contact form where you can send us lots of information and just say hi. If you want to support the show, there's a bunch of different ways you can do that. You can give us a review and a bunch of stars on your podcast catcher of choice. It's a really good thing to do because it helps us to rise up through the noise and helps other people find us and share in just the complete geeking out on all things cosmic and astronomical. The other thing you can do is go to patreon.com and become a patron of the show. Sling a few pounds our way to help us keep the lights on and the electrons flowing through the website. But even if you don't do that, just continue listening, because we'll be back again in a week or so's time with some more cosmic goodness. Until then, catch you later, Emily.
See you later.
Bye, everybody.